world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the
All right, hello and welcome everyone to Aether Roundtable 125. Tonight we're going to be doing a recap on how math became reality, starting with just two of the proofs for general relativity, and we're also going to examine the mathematical framework of general relativity to see if it satisfies the conservation laws that are so beloved by mainstream physics. So to get us into gears here, we're going to do a quick recap on kinematics and dynamics, as there's going to be a huge distinction between the two throughout this presentation. That is a key point of it. We're going to review the experimental evidence for general relativity, which is the perihelion precession of Mercury and gravitational waves. These are the things that got the theory's foot in the door, so to speak. So we're going to take a close look at this whole historical narrative. And we're going to keep a close eye out for dynamics, which we'll get into in a second. And then we're going to review pseudotensors so we can review how Einstein is using his mathematical framework within absolute differential calculus. And we're going to see if he's following the rules. So kinematics and dynamics and the perihelion advance of Mercury is going to be Act 1. So to start us off with Act 1, we're going to refer to our Shankar physics book, who gives a nice brief definition of what kinematics are, and it is the complete description of everything that's going on right now in a system. So for example, if somebody throws a baseball at you, you're going to interpret where that baseball is going to be over the next few seconds based on where it's currently at. And as it's changing position over time, you're tracking it, you're adjusting where it's going to be. And, that real-time relative motion is how you're interpreting the prediction of where the object is going to be in the future. The equations that govern kinematics are all distance over time related or derivatives of a component of that. And that's what allows them to determine like acceleration or, change in position over time is essentially all that's going on there. There's no accounting for forces or mass, or you're not concerned with how much something weighs or friction or anything like that. Just position over time strictly. And to note, in kinematics, relative motion is always true, especially when you're doing an analysis. So in that baseball scenario, you could equally say that the baseball is stationary in the sky, and you're moving towards the baseball at the same velocity that you would be observing it as if it was moving towards you. So those two representations, those two descriptions rather, are equally valid in kinematics. Now, in dynamics, you have to make future predictions of motion based on actual forces. And to do that, they always start with the lab frame, and then they go in and account for things like friction, force, mass, all that kind of stuff. Anytime you see mass in an equation, they're talking dynamics. They're making a prediction based on real quantities that will affect the formula involved. So when you're solving for how much force there is, a factor is that is mass times acceleration. So that relationship of mass creates that dynamic force there for how much force is required to move an object or how much force it has, etc. All of that is going to be contained in dynamics. So one's only concerned with relative motion, and the other one is concerned with actual forces. Huge distinctions. And to be in aligned with dynamics, your predictions have to satisfy conservation laws and energy prediction laws. So when I said earlier that predictions with respect to the lab frame, why they start there, that's because all the motion of a system can be analyzed with respect to the stationary lab frame. And so that's the only frame that can actually make the correct predictions for everything. So that's why that works out the way it does. So in astronomy, there are a series of fundamental constants that are put forward. So we're talking speed of light, the big G, the gravitational potential constant, and all the variables that they use for mass in all their equations So anytime you see GMM over R squared, that'll be, oh yeah, R. So radius value, the radius of Earth. There's a couple other ones, but the ones we're primarily going to be dealing with were the ones that I just listed there. And so ideally you would want to have a way to confirm, all these constants independent of one another. But what actually happens is that they're all used as a ratio to confirm one another in a way that becomes where it creates a internally consistent system of self-referential constants. And in that, um, you can't really get the wrong output when you use an input, or when you put in like an observational input. All the outputs are going to be ratio based. So you're going to get all the proper units and everything based off of periodicities, for example. And that's going to be a huge point to understand as we move forward, is that all of these variables together make a system, and independently they don't really have any measurements for them. Like they're always confirmed through a relationship of another one of the constants. So a primary example of that, like we were just talking about, was GMM over R squared, which is Newton's dynamics for solar system dynamics. So with that equation, we've got the gravitational potential, we've got the mass of two planets, we've got it falling off over the square of their distance apart. And so with that, it's kind of asserted that these planets weigh this much, and the gravitational potential between them is the cause. So therefore, this planet must weigh this much. There's this much potential between them, etc. That's what causes this planet to move at this velocity when it's this far away to complete this orbital path. That's the way that they interpret it. But the equations that came before Newton were actually Kepler's laws, and that's just converting the velocity into distance by using a ratio of pi and the periodicity. So you can solve for velocity with distance over time. And with those components, you can establish, orbital parameters. So when the Kepler's laws were first introduced, he noticed that the square of the periodicity is proportional to the cube of the semi-major axis, this R here. And the semi-major axis, of course, is the horizontal line that intersects the center of an ellipse. So the proportionality there for how long it takes to complete the orbit is that. And for every single planet that orbits, there's a constant ratio here that pops up when you do that ratio. And it's based off of where your center point is starting. So because they interpret the motion through the sun, they can solve for what the sun's mass is based off of the orbital potential, based off of the velocity created by the orbit for this planet. So to kind of look at this the way that they did it before Newton and before Cavendish, what they have is they have a unit for the semi-major axis that comes out of the periodicity and pi. And then but it's dimensionless, right? It's an astronomical unit. It doesn't have any meter association with it yet. It's just an abstract concept. And then they have the periodicity. So they've got a unit number for distance, and they've got a periodicity here. The ratio between all of these is this number here. So when we look at this graph and we see that this maintains a linear relationship, but it scales, exponentially, we like that's why that relationship is linear like that, because it's just all just a constant ratio of wherever you start your center point. And so with that, you could ratio these two numbers together by multiplying them by pi, and you could get the gravitational potential and the mass. But the two are combined in this, so we need a way to remove the gravitational potential from this, so that we're just left with the mass. But we don't know the gravitational constant yet, because Cavendish hasn't done his experiment. So all we can do now is have this abstract relationship between um, what the center body is doing in relation to the other bodies to create the periodicity that they're experiencing. And then Cavendish came along and measured the deflection of two lead balls, asserted that that was the gravitational potential of the Earth relative to the lead balls. And then that once you have that relationship, you can now divide this part here, which is just a ratio of distance and time, to get their quote unquote mass. You just divide out the big G here. So that's what we're doing. And what you get is the mass of the sun. So that's what they started with. And then to get the mass of Earth, you have to use, to make that the center point, you have to use, an orbiting body of that. So they take, in their cosmology, the moon orbits the Earth and not the sun, or whatever. So the way that they break it down is when they ratio it against Earth, they get this mass number here. So this is how much Earth must weigh to create this gravitational potential and mass relationship to create this, to create the periodicity of the moon, that 27.5 cycle or whatever it is, 27 point something day cycle. All of that is created by these ratios. Now, the important part to remember is that all they have is a periodicity and pi. That's all they started with. So all these other ratios and all that came out of it afterwards is just ratios using other constants to relate physical variables. So introducing G here gives them kilograms. So once you can introduce kilograms to this, you can now give meaning to this abstract ratio here that you got out of multiplying the what was it? The periodicity times the semi-major axis. So that's how they came up with the whole thing, and that's how all the distances and masses all work out based on purely kinematics. No dynamics at all until they started dividing by G to get in their unit there. And then once they have that, they can start they say, okay, well, we're going to solve F equals GMM over R squared. Well, this is a closed loop here. You can't solve for one of the M's in this. If you try to solve for one of the M's, you're going to swap in the F. To know the F, you already have to know GMM over R squared. And to know that, the masses have to cancel out, and it defaults back to a ratio of the original periodicity. So that's how it always falls back when we talk about the mass canceling out. That's what's happening there, and that's why it cancels out, because this is a closed loop. The constants don't matter at all. It's always about the periodicity. The G and the M there are just there to convert units for us to give it a relatable term, because we can, we have a concept of how much I have a concept of how much my phone weighs, right? So we can talk about that in kilograms, pounds, etc. But when we talk about how much, how a planet's moving, like how do we conceptualize what that force is doing and how that relates? Well, to do that mathematically, they got to get in something that has that unit variable, and that's basically what the constants are doing. They're serving as unit conversions, not as any sort of dynamic cause, because to solve any of these equations, you have to cancel out the mass and always divert back to the original kinematics. And we're going to see that play out as we continue, as the mathematics gets more advanced and they start introducing tensor calculus and whatnot. Okay, so we're going to take a quick stroll through some outputs here from a Python script that's available on the GitHub. All of the information here is all on the Obsidian, and then the Obsidian has the GitHub and the Python scripts and stuff. So if those need to be reviewed or whatever, you can find all that there. But like I said, when you start with the center of what you're talking about for the orbit, so they're making it all related to the sun. The way that the ratio comes out, you get the mass of the sun, and then to solve for the Earth, you get a different mass, and it's based off of the reason that these two are different is because they're setting a different center. But in our cosmology, we would say, the Earth is at the center and everything else revolves around that. So what would that look like? Well, the only thing that would change is we would have to change the distance of the moon by solving for the moon's distance using the other orbital parameters. And once we do that, the ratio will go back to being 1, like it is with all the other variables. And we can also backwards solve for what the Earth's mass would be based off of the same thing that we did earlier, with Earth being the center of all the orbits. And then that would be, it would give you what the ratio of the masses to the sun is said to be. So there's no difference between these two um, in terms of relationship. Only the only thing that would change is the relationship to the distance of the moon, so that it'll scale proportionally. I think Shane did a presentation recently where he covered how they use scale invariance for the solar system using angular size and distance relationship. This is the same exact concept. Everything would scale proportional based off of one factor changing, but that one factor changes, throughout everything else, and it makes it all proportional. So we could, so here we have what it looks like when the sun is the center mass, and we have all of the astronomical units here, and then we have all the astronomical units here when we swap in the Earth. And what do you know? It turns out to be identical in this. Um, because it's just the same exact periodicities and places and whatnot. So when we swap in Jupiter to be our center, that has a different periodicity to the sun. So that's going to rescale all the distances, but the ratio is going to remain the same. So we see here how the astronomical unit will scale different relative to everything else if we make Jupiter the same, but everything is observationally based off of the periodicity. So how we view everything in the sky, nothing will change. Only how we perceive the calculated distance. If we were to say, how far is Jupiter in relation to us right now? How far is Saturn in relation to us right now? Well, only that would change, but the time and position in which it's at would not change. Showing that relationship here, here's what it would look like with Mars in the center. Same thing, just changing the distances. Everything else scales proportionally. With distance as your free parameter, you can set up whatever. Now, the beauty of discovering this relationship first is your distance is your free parameter inherently. So if you take that as your accepted known physical value and build everything off that in relation to that, well, guess what? You're always going to get back to your starting point and be self-referential and internally consistent, because it's always based off of observation and time. So it's not going to construct anything physically meaningful, but you will have the numbers to calculate those distances should you feel so inclined to assign a physical distance to, help illustrate your conceptual model. All right. So with all of that, so keep that in mind here, that none of this is like mutually exclusive. It's all math ratios based off of observation and assigning constants where they fit in to give us units. Now, within that framework, they started to establish heliocentrism. They said that the Earth, based on their philosophy that the Earth's in motion, et cetera, et cetera. They keep all these astronomical observations and things for their model, and refine it and track how accurate they are. And we know how obsessed they are with getting the values as exact and precise as they can. Like sometimes they get down to like, 14 decimal places on something, which is just, it's a little lengthy if you ask me, for in terms of like 14 decimal places on weighing a planet, when the gravitational constant measured on Earth only goes out to like, I think 4 decimal places or something, but they end up with an even higher accuracy for the mass ratio when they ratio out everything using the lesser value. So that's cool. It makes sense that it gets higher somehow. Um, so within this framework, where the Earth is rotating, chasing the sun, etc., uh, based on their elliptical orbits, those are closed systems, so there can't be any um, differences in where they would be positioned over time wise, essentially. And so, uh, or what was his name? Hervé uh, Lever made some. He was doing an analysis on the positions of Mercury over a century, and what he found was it wasn't quite in the location that they would predict over time. Now, this isn't something that you could ever observe. You're never going to whip out your telescope and be like, "Oh, Mercury's 0.002 arc seconds out of position." You'll never, that'll never happen. You can't even get that kind of observational accuracy. This only comes out of statistical computation. Okay. And then so what they do is they subtract out Earth's rotation, which they would interpret as wobble. So we would be seeing, so like the possibility that we might be seeing Mercury out of position is because we're wobulating. So we're viewing it from a slightly different position than what we should be. So that would be like one potential cause. So they subtract that out. So that makes the Earth stationary. And then They subtract out the observed deviation that it has naturally, and then also they subtract out the summation of all the gravitational potential perturbations for all the other planets. So basically, if there was like a little celestial tug of war going on, they're accounting for that, and then adding all that up together and subtracting it out, and then they're left with 43 arc seconds. Now, when this was first calculated, it was only 38 arc seconds, and the guy that originally calculated it used, oh yeah, Laverne, he used the wrong mass for Mercury, and he was slightly off on Earth's mass by like 6% or something. Now, when the values were recomputed by Newcomb a little later with more quote unquote accurate values, they got 43 arc seconds. So 43 arc seconds stands as their official value that they have. So we're gonna, give them the benefit of the doubt and work with that before we even get into other issues with that. But let's just assume that this is real, and now they have to account for it, because what this means is the Newtonian orbit, if they're going to assert Newtonian dynamics for ellipses, there can't be any sort of perturbation like that, or perihelion advance like that, where it's going to be in a different position, because that would imply that there's energy that's not being accounted for in the system. So they took all the factors of what would cause that in the system, subtracted it out, and had a leftover remainder instead of zero. So they were like, we don't, we have to solve for this, otherwise conservation isn't being upheld, and that's fundamental to our physics. So at this point, to look for this solution, they're saying, we need to satisfy conservation laws. So keep that in mind, that when the stakes are right, are this, they're looking for a solution. So there's two possible solutions that they could go for. There's Gerber and Einstein. So Gerber in 1989, 18 years prior to Einstein's published solutions, Paul Gerber used an equation to solve for the perihelion precession amount. His hypothesis was that gravitation propagates at a finite speed, and because it's propagating through a medium, and it's the same medium that the speed of light is propagating through. Therefore, the speed of propagation of a gravitational wave will be the same as the speed of light. So if you take this equation here that he got, he started with the differential equations for motion, for Newtonian motion, pulled out the ellipse, did satisfied conservation laws by cross multiplying out vectors, and let's see, as he reduced everything down, it came down to kinematics, essentially, because it's just this equation here. This mu represents GM, which is going to be the asserted dynamics. But when you go to solve this out, it ends up just being the periodicity ratio again. So that's all that represents out. But anyway, the way that Gerber solves for the speed of light, he solves it through the orbital parameters of of all the known factors that they have. So they got the value of the perihelion advance itself. They got the eccentricity of the orbital parameters for Mercury. They have the semi-major axis for Mercury. They have the ratio of its periodicity here, and then they times pi, and this is just factoring in the ellipse geometry, essentially with the periodicity to the semi-major axis. And so when you solve for that, he got the speed of light within 0.02%. And that's incredible, especially if if you don't realize that all of the parameters are all based off of internally consistent ratios, starting with the speed of light and Earth's radius and whatnot, like how they put the meter to the astronomical unit by doing it during a when Venus was in a particular part of its orbit, to create a central angle triangle to the sun that's starting from an observer at the center of Earth. They used Earth's radius to get a fraction of the astronomical unit, and then multiplied it out to what it would be to complete it to the distance to the sun. And when they solved for that, they got 93 million miles. So that's the speed of light is also uh, the wavelengths are measured in meters, and meters are a ratio of a terrestrial meridian, and a terrestrial meridian is defined by Earth's radius. So what we're seeing here is the output of an internally consistent system, where they have related units of measurements in meters to distance over time, And when we get, so it's an awesome output the way that he was able to derive this, but this is the product of an internally consistent system using ratios of constants over with periodicities. It's not like um, he didn't actually like independently derive this. It's already a parameter that is part of this framework itself, and we're seeing it come out as an output, but it's also part of the inputs. So solving it is circular, but to see it out like that is pretty awesome, I must say. I was pretty blown away when I saw what he was doing there. So this was, again, keep in mind, this was after the Michelson-Morley experiment, where they had decided to move away from the concept of a static elastic ether because they didn't get the velocity component that they needed for the Earth moving through that ether. So they were kind of apprehensive to accept this explanation, even though mathematically it is sound AF. So we're just going to look at what, the parameters here, and then what he solved for, just to kind of look at what it looks like when you solve it out. And then you can also reduce it to a purely kinematic form here. So no dynamics at all. So in the reduced form, you can solve for the same thing and get, we're solving for the angle here, but in any case, um, that's what it reduces down to. So it's all kinematics and relative velocity, essentially. Um, so yeah, that's how all that works for Gerber's situation. So that's what he put forward under the ether model. And so Einstein comes along in 1915, and he's like, "Hey, these are my field equations on how I'm going to describe Mercury's perihelion precession." So he starts with the field equations here, and I'll zoom in a little bit so we can kind of see what these look like. So he starts off with these field equations to describe uh, the mass and matter of this, or the mass of the sun, how that conserves into a gravitational field, how that gravitational field bends space-time, how that bent space-time geometry is going to change the orbital path of Mercury such that it is 43 arc seconds out of position. So he starts here, goes through his derivation. By the time he gets to equation 12 here and equation 13, he says he's going to go ahead and just, to solve the rest of it, he's going to just replace mass, the GM, with Kepler's laws and finish it off with that ratio because it'll be quicker to solve. So he reduces it down to the same equation that Paul Gerber used, but we'll take a closer look at that in a second. We have to look at another issue. So in here, you'll see he has two integrals going. And what he did was he split the Newtonian orbit from the predicted gravitation, or from the predicted space-time, orbit. And the space-time orbit is going to be affected by a factor of alpha times x cubed. And what that's going to give him is that amount is the perihelion precession. So what he is doing is changing the orbital parameter essentially by that amount for the general relativity theory. And in this integral, he doesn't change the root for for the Newtonian one. So the Newtonian one predicts, half of what relativity theory predicts. But the reason for that, what we find out later from Schwarzschild, who corrected the math done here in this very paper, and also by another man named Vankov, is that the when you split an integral like this, when it's over the uh, same orbital thing, or it's the same orbital parameter, you have to change the root, which is the 0 point in over this integral where the orbit is going to change from perihelion to aphelion. So basically, like the 0 point of the orbit, where it's going to be either going towards or away from the sun. And he only changed it for general relativity. He didn't change it for the Newtonian orbit. So having two different roots, when he compared them, he's like, "Oh, look, we predict double what they predict. There's a deficit now." But if you correct the Newtonian deficit, it cancels out, and they actually don't predict anything from these field equations. When you do the math correctly, this what Einstein proposed as a solution doesn't actually predict uh, any precession. But remember, he did separate it into another. He did say like, "Hey, we're gonna stop here. which ends with his integration stuff. And then he's like, we're going to substitute in kinematics and solve that way. So he's actually got two solutions in here. One for GR using dynamics, which he bailed out of, didn't math correctly, and then actually predicts zero. Now you can do it quote unquote correctly, which Schwarzschild did, and then he got the proper 24 using or 43 using the mass. But this way, the one that's given as the proof here is not it. So anyway, we're back to what Einstein used for the kinematics here, and instead of solving for the speed of light, right, he assumes that the speed of light is a constant, so he's going to use the 43 arc second to solve for that. And because he changed the orbital parameter of what general relativity is using here in this a squared, when he solves for this, well, what do you know? He gets 43 arc seconds, and therefore, it's correct. Now, keep in mind, this one was quote unquote correct, equation 14, whereas equation 12 and 13 do not lead to or I'm sorry, equation 12 does not lead to the correct answer. Schwarzschild had to fix that. So this is from Vankov here talking about the integration issue, and then this was also pointed out by Schwarzschild. Now, Einstein said in his paper that he assumed that because it was such a small amount that it wouldn't make a difference, so he didn't bother applying it to the Newtonian one. That's what he said why he didn't apply it. But when you apply it, this is what happens. It predicts a zero, but it realigns the roots so that it's an actual comparable integral. All right, so showing that, so just kind of showing the math on that here. We've got the dynamics for what they would assert. We got the periodicities. We got their ratios for their perturbation parameters. And then we have the integrals here. So we see that this integral is going to lead to an ellipse when they apply the proper dynamics to it. And then this integral here has an adjustment of 3 pi alpha over 2 pi, or over 2 p for their semi-lattice rectum. I don't know what that's supposed to mean, but this is their semi-major axis. um, so putting it over that is going to give that change in the orbit, which will give them the 43 arc seconds that they think that they predict. So that's how all that worked out. When you correct that parameter, when you do it correctly, it comes out to be zero. So there's no actual prediction there from the way that Einstein solved those equations. Now, Schwarzschild came in and fixed that situation there, solved them a little differently, and used basically, he rounded off the infinity by using a convergence technique. And then, so with those parameters that he established through the field equations, which is consistent within the framework, he solved that. And, with the quote unquote dynamics, which actually ends up canceling out anyway, regardless of whether or not you want to include it. But, he did try. So, anyway, when you solve it that way, it comes out to 43 arc seconds. All right. And then again, looking at it in the regular form, like the long form, and then the compact form there, like to reduce it out to what it simply is. It's all just kinematics. It's just a ratio of periodicity and geometry, essentially. It's what it's always been. No one's ever had anything differently. It's just in modern times where it's asserted that all these things are, physically correct, and we're going to the moon and we've been to the moon. So therefore all these distant, all of that is based off of this model and making it be interpreted as physically correct, even though it's always just been geometry and periodicity. So a quick summary here of the predictions and the math involved. Zero dynamics were harmed in the making of these solvings of these equations. All right. So we went over, let's see. So yeah, just illustrating that mass was never needed to solve any of those equations to rectify their problem that they thought that they had. They only had to rectify it because they were asserting dynamics, and then saying like, oh, well, we satisfied conservation laws, and then to find out that they didn't is a huge slap in the face to them. So that's something that they feel compelled to rectify. Now, it should be noted that there are no uncertainty errors for the measurements of the analysis on the perihelion, of the measurements for Earth or the mass of the sun, and any of the comparisons. So when those are done, De Sitter did an analysis, and there was a guy at the Royal Naval Observatory. It was, how did I miss that guy? Who is he coming up? Um, well, anyway, there was a gentleman at the Naval Observatory who was in charge of calculating all the orbital stuff and and tracking their positions and stuff. And he talks about this air situation where if you take the potential air for Earth's wobble and the the normal perturbation that Mercury, is observed, if you take those airs and add them together, it's bigger than the 43 arc seconds. So what they're potentially trying to solve for might not even exist. But nevertheless, they calculate. So Act 2 is going to be gravitational waves and absolute differential calculus. Okay, so uh, black holes and gravitational waves are things that are said to be physically measured through not only the observational influence of when a planet or star or galaxy or what have you isn't following uh, the normal, its normal speeds, and whatever. They're like, oh, there's a black hole nearby, and they just introduce the mass of that black hole to solve the scenarios. So they're like observationally plugging it in to confirm it. But they also have interferometers, primarily LIGO, established to measure so-called gravitational waves. So we're going to look at how they calculate these waves in a medium, or I mean, sorry, in a vacuum that's supposed to be empty and just filled with space-time, which is explicitly been said by Einstein over and over again. You can think of space-time as a medium, if it helps you conceptualize it like a fluid medium, but do not assign physical properties to it, because it's just, it's a conceptual manifold essentially. So you can't have any physical properties to it, because if you assign physical properties to it, all motion is going to be relative to it, and then you're going to have to explain Michelson-Morley all over again. So that's the conundrum that they're in. But anyway, so they got this vacuum, this Newtonian vacuum of space, and they've got these gravitational waves. So we're going to find out more about how that relationship works out, especially in the math. Um, so yeah, so what we're going to find is that waves require a real medium to carry momentum and to propagate. And because there's no medium in space, and the way that the field equations work with canceling things out, and the equivalence principle where a gravitational field can be canceled out arbitrarily at any under any transformation, um, he had to do some trickery to satisfy the conservation laws. So we're going to look at what happens with that and what happened when he was called out on that. Because remember, at the beginning of the presentation, the whole point of figuring out what was wrong with the perihelion precession was that they had to solve conservation laws, because without them, the Newtonian dynamics would mean absolutely nothing. So, all we must uphold the conservation laws, and Einstein must do the same. So in the 1900s, Levi Civita and Ricky Cabastro published a theorem of and a framework of absolute differential calculus. And the purpose of it was to preserve real quantities and make them invariant under transformation, and anything that's arbitrary and not, not an invariant, not a physical quantity would just, would fall out. And so the framework has specific rules and whatnot that are set for it. So we'll take a look at some of those in a second, but we're going to look at some of the field equation stuff to kind of get familiarized with the notation that's used in absolute differential calculus. So it's written in letters, of course, in Greek letters. With these are called indices, these upper variables here. So these tensors have indices on them. So the tensor would be t, the indices would be mu and nu. And what these mu and nu encode is a 4x4 matrix that describes the density of energy, the flow of energy, basically any parameter you would want to know, like hydrodynamically, essentially, in regards to energy and like flow and motion, it will be in that. And all of that is going to get conserved into a gravitational field, which is going to curve space-time. And that curvature of space-time over here is going to affect the path and trajectory of the metric over here, which describes distance and angles for 2 points on the manifold. And the manifold, of course, being space-time. And then the 8 pi g over c to the fourth is just describing that, like how much gravitational strength there is per cubic centimeter. You can kind of think about it like that, it's establishing like that density gradient of the field over the manifold. All right, so that's what that looks like. So you don't really need to go any further to conceptually uh, grasp the arguments as we move forward, but this is just a quick overview of what those equations look like in modern form. They look a lot better than what Einstein wrote down originally, so I'm glad that the notation has improved. So a familiar metric here that Einstein uses for flat space-time and curved space-time is the ds squared. So you'll often see ds squared being used, and what that encodes here is the x, y, z parameters for space-time, and that this would be flat space-time. And then if you see the metric g mu nu here, and the dx mu and dx nu, those are curved space-time. Now you can use curved space-time and then but set the curvature to flat, so you can like also still use this while describing flat space-time, and that can kind of be very deceptive because you're using what would be implied as a curved metric on the surface, but then when you go to solve everything, you're actually just flat. So you got to keep a lookout for that. Sometimes they'll sneak that one in there. So in their preface of their paper, Levi and Ricky talk about um, how the purpose is to preserve invariance under transformation, and physically meaningful quantities will preserve their invariance under arbitrary transformation, and that's basically it. And um, um, if you want to conserve energy and momentum or use like invariant properties, they give instructions on how to construct your own tensors, and how they can how to keep them, how to make them remain invariant under transformation. So we're going to take a look at some real tensors versus some fake tensors. So G mu nu, real tensor, just gives the distance and angles to 2 points on spacetime. G mu nu, that's their gravitational spacetime curvature tensor, or sometimes called the Einstein tensor there. Relates, anyway, real tensors here. And what makes them real is that when you extract them out, their components of what they're constructed of are made of second order derivatives of other components. So because they're second order, when they transform, that's what keeps them invariant under transformation in this framework. If they were derived from first order derivatives of other variables, when they transform, they would not be invariant under transformation, they would drop out. And so when these are properly constructed with second order derivatives, these have been extracted out, analyzed, etc. These are all good. Now, Einstein, like I said earlier, um, he had to describe a way to conserve the energy of the gravitational field, um, where it's going to be canceling out. So he had to introduce a new tensor to do that. And in doing that, he came up with this here, the lowercase t mu nu. And when you extract that out, what you'll find is that it's constructed of pieces of the Christoph symbols that make up the gravitational field itself, and then also first order derivatives of these metric tensors here, and they have to be second order derivatives. They can't be first order. And so he doesn't do that properly. And when he solves for or when he does it with this, he ends up restricting the theory. So the theory was first, the framework when used properly, arbitrary transformations will produce invariant quantities and everything will be preserved. Now Einstein's saying, hey, this tensor is only going to work with certain transformations that are linear. So he so he took the framework, broke it, presented it in a lesser form, and said, this is how we have to use it now. And then later, Landau and Lifshitz constructed a tensor to try and conserve angular momentum, and they end up doing the same thing, which we'll look at here in a second. Now, the creator, or one of the co-creators of absolute differential calculus, made his own tensor showing how to do it properly with the using second order derivatives of the other tensors. And when you do that, you can't, when you cancel, it conserves momentum by subtracting it out essentially whenever there is any. So what it does is, in the presence of a gravitational field, it gets subtracted out and conserved, but this can't lead to gravitational waves. This can't lead to a finite propagation speed of gravity through a nothing medium. Like it's hand in hand a component with how they try to describe the perturbation of Mercury, as well as black holes and whatnot. So they they can't really use the one that doesn't lead to that solution, so they've just ignored and disregarded that and kept using the broken one that doesn't conserve anything and removes any potential for physical meaningfulness out of the framework that Levi and Ricky made. So they go over that scenario here where they talk about um, the tensors and how, if they're constructed from a first order derivative, they will not be invariant under transformation. They will disappear, vanish under certain conditions, etc. And they don't preserve the invariancy. So if you want to construct a tensor, you have to use second order derivatives, etc., etc. And then in a following paper that we're going to look at, we'll see what a proper one constructed, how it gives the answer for zero. So for general relativity here, Einstein published in 1915, along with his perihelion solution, the field equations for gravitation and how they relate to the bending of light for light around Mercury. And so in this paper, he talks about how the covariant linear relationship for the special theory was awesome, and he's going to extend it to covariance for all systems of equations. So instead of just linear velocity and also being stationary, so-called, or what they would interpret as stationary, being in linear velocity, um, he's going to extend it to acceleration, rotation, and gravitation. So any reference frame, he's going to be, he's like, we can do anything. But then he uses this tensor here, which he later goes on to show and talk about how it's impossible to do it under certain coordinate system transformations, and et cetera, et cetera. And we see what the tensor looks like extracted out here. And we see it's comprised of first order derivatives of the metric tensor G mu nu. And these Christoph symbols here are the gravitational field itself. So these will not lead to an invariant transformation as per the framework of absolute differential calculus, but he still tried to do this. And a little bit later, he republished a complete version of the field equations with the perihelion solve and the light bending for what was it for the for light bending during an eclipse and all that. So he combined all of those, wrote everything out. And here, same exact scenario, nothing changed. He didn't fix this, and he knew about this prior because like 3 years before he published all this, and while he was working on it, he was in communication with Levi, who kept showing him consistently how, under the transformations proposed, that they still don't lead to invariant solutions, and you can't use this tensor because it's leads to non-invariant transformations. And Einstein just kept saying, well, I still kind of feel like I'm correct, and I don't really want to acknowledge your point because then it would undo all my hard work. I'm not really ready to let go of that. And then he later admitted to understanding the issue and grasping it when Herbert Dingle wrote him, confirming the same thing and showing him the example at an earlier part in the equations. And then he was like, oh, well, that makes sense. Yeah, sorry. And then, he just never corrected it because you can't correct it. There's nothing to correct. It doesn't work within the framework. So anyway, he's talking about it right here, how it doesn't do anything for the conservation laws when done under non-specific transformations, which defeats the whole purpose of the framework. So Levi comes in and derives his tensor, and then showing that when uh, the conservation tensor Timu nu, which is TIK in this because it's the old notation for it, but anyway, when these two are together, the momentum is, or, the energy is subtracted out, and it's conserved. So the gravitational field leads to no gravitational waves. So they had already been establishing, the use of the gravitational waves and the bending and warping of space time and the distance relation, or I'm sorry, the time, the propagation rate of all of that. So they're already locked into what they needed, so they could never acknowledge this. So this was published in 1917, 2 years after Einstein's 1915 paper, and it was never picked up on or explained, or by anyone. And he shows here in section 9, the title is "The Misunderstanding," or Einstein's misunderstanding about the gravitational tensor. So he goes through and shows here how when you extract his tensor, it's comprised of all the invalid components to be at first to preserve invariance under transformation. So we got the G mu nu in there, and we also have the curly brackets, and the curly brackets were the old notation for the Christoph symbols. So none of this is going to yield the correct results under transformation. And then in later years, in more modern times, Stephen Crothers was doing his PhD candidature on an analysis of general relativity. And when he was doing that analysis, he found the same exact situation when he constructed Einstein's pseudotensors, and found that, it has that problem that Levi originally pointed out, and there's no solution for it. No one's tried to do anything except for the Landau and Lifshitz guy, or gentlemen's, and those two guys made the same exact mistake here. But what we're looking at is all the components that were, or just like, all you need to know here is that there should be a derivative symbol here with a second, uh, like a number 2 on it to show that it's a second order derivative, or it would be right here on the, like, before the t to show it. So the way that they do the notation is they can put it before to encapsulate all of it, so that you don't have to write it out and have all these symbols stacked on symbols and whatnot. But in any case, it's not here, so invalid. And then same thing for the Landau Lifshitz one. When you contract out their tensor, it shows the same exact relationship. It's made up of the Christoph symbols and the G mu nu component itself. So none of those are going to lead to a actual physically meaningful transformation in their framework. And for any of these equations to have any physical meaning in their framework, they would have to be satisfying conservation laws. They'd have to be adhering to these things, and they never did. They never will. And so to kind of end on that, there's no theory that explains this 43 arc second difference, and it might not even be a real thing. When you apply the original gravitational, when you apply the original gravitation field equations uh, to solve it, how Einstein used them, it was incorrect. When you apply them correctly, how Schwarzschild did it, they give the correct answer. But sadly, 4 months after Schwarzschild made that correction for Einstein and published those, he passed away due to an autoimmune disease, and his equations were reinterpreted in the textbooks. And so the r that he used as a radial vector to describe the distance, he was transformed into a radius value of the point that's established when you have 2 points on a graph and you draw a line between them to, graph out that line. Well, they made the r the center of that point, which is, dimensionally invalid. You're putting an r on a component that's not a physical value of anything. It's a point on a graph, and so anyway, when they do that, it essentially breaks down, and gravity near that, breaks down, and it breaks down at the center point of it. So what they ended up doing is equivalent to dividing by 0, and then going, oh my God, the equation broke, and then turning the broken equation into a mythology onto why it broke as a function of the collapse of gravity because there's so much gravity there. It's compressed into one tiny area, and when it's compressed like that, it breaks. Well, that only happened because they changed the definition of a radial vector to a radius, and then made and then also removed whatever he did to do the to remove the divergence to infinity. Whatever rounding he did for that, they removed that. So the reinterpretation of what Schwarzschild did leads to physically meaningless nonsense because you turned a radial vector into a radius value and then broke everything. So that doesn't mean anything either. Um, so there's no actual admissible solution for gravitational waves in a vacuum other than what Levi posted, and that solution leads to no waves because it turns out you can't have a wave in nothing. So after 108 years, none of this has been resolved, and physics is just as like the end result, like the we're stuck in the maximum conclusion of uh of taking these ratios of constants and trying to build a physically meaningful framework out of it. You know, like, oh, we're going back to the moon that we went to and confirmed the distance to, but they just can't do it. But we're halted, we're retarded by this whole cosmology, this whole mathematical framework here has led to nothing because of the philosophical belief that the earth is in motion itself and trying to give physical meaningfulness to these ratios, to this ratio here, to make it into a conceptual model. And then just telling everyone that that model's conceptually real. It's not a concept
Neat. Where
anymore.
do
It's
I where do I sign up for this mythology? Can I get some lore books? Is there like a ceremony or
yeah, yeah, yep.
I'm in?
All right. So if there are any questions or comments, the floor is the floor goes to you, lads.
I mean, what else would you want to build a mythology upon unless it's a collapsing mathematical function, right? Like what else is there?
Well, this is definitely very unscientific science.
Well, dude, speaking of unscientific science, you know what you could do too, since we have this ratio of periodicity and no actual dynamics. What you could do is um that guy Dr. Shiva, God bless him, posted the a really cool polar coordinate transformation for where the angular position of the sun will be using polar coordinates. And so like what we could do with that is do the same thing and then have it be like where the positions will be angularly on like a AE map and have it kind of show that same relationship because it's all just kinematics or whatever. You using the AU as the distance or whatever, but if you rescale that, it doesn't affect anything. Oh, that's what I wanted to show real quick. Speaking of rescaling. Okay. So earlier when I said that Paul Gerber, when he solved for C, that was really impressive because it gave the modern accepted value for what everything is based upon now. Okay, but let me show you guys this. Here. What am I trying to run here? All right. Pure healing. Calc. I think this is it. Yep, here we go. Okay. So if the radius value were different, right? Then everything else would scale out proportionally. And then when you solve out that same equation that he did, the ratio to C solved, when he tries to solve it out based off of the new orbital parameters, gets a constant ratio to what the accepted value is. So it just scales proportional to whatever the astronomical unit would be. So when he solves it using the new value, the speed of light would just be it would change like this. So if it was 7,000 kilometers, you would get 200,000, 272,000, so on and so forth. 12,000 kilometer Earth would give 160,000 kilometers a second. So anyway, I just wanted to show um, how those constants would change in relation to that meter being changed by the definition of Earth's radius, and then how that would relate to what they derived for the astronomical unit, and how everything would scale proportionally. Nothing would change in reality. The wavelength of light would still be the same, but the way that the ratio of its meter would be, interpreted through the radius. So it would just
Neat.
rescale that 1/10 billionth factor.
How tidy
So
and elegant.
yeah, it's so awesome, dude. I was so blown away that he solved for C like that. And then I was like, wait, how did he do that? And then thankfully, your presentation provided the solution to that, the one about the measuring the physical distances
V
using
over V or
radar.
whatever.
Yeah,
Yeah.
you crushed it. Like the backbone of all of that, central angle based on the ratio of assuming the known distances to start the triangle, and then solving for what it would be. I mean, dude, that's literally all they did. And then you could see how that really how you can see how their interrelationship plays out over an equation solved over periodicity when you try to solve for one of the parameters when you only know, all the other ones. And it's like, oh, surprise, you get the missing variable that's compatible with what it would be if you tried to solve for any of the other ones.
Didn't they do the same thing with aberration angle, right? Like the 20 arc seconds, and then it's like alpha. I think it's like tangent 20.5 arc seconds equals V over C. You
Yep.
get 30 kilometers a second. So then they just do tangent 20.5 over V over 299 million meters per second or whatever, and then solve for V, and then you got V equals
The-
AC, and then because of the speed of light, you get V equals 29.8 kilometers a second.
So
Hmm.
that's really interesting that you brought that up, because solving for the angle or solving for the speed of light using the angle, excuse me one second, leads to the speed of light. Okay, so using a geometric relationship to the relative velocities, you get this. You can derive either the speed of light or the geometric angle. Very, very cool. And that's in air. So they add water, right? And then they don't get the angle that they need. So they throw out that relationship of geometry and relative velocity. And they say, okay, well, if we transform to a reference frame on the sun, and to get these angles to work for that reference frame, we have to accelerate the light. So they predict in that reference frame 15 arc seconds on the sun frame for the water, and then 15, and then if you make the sun moving, it'll actually, hang on, I can pull it up right here. I was just looking at it earlier. Give me one sec. We can look. I don't have to try and recall it. I can just we can just look at it together. Okay, so zoom out a sec. Actually, let me just move this so we can have it closer. Copy. Just put that right here under the
Oh, dude,
classic.
you have a whole V over C spreadsheet. I didn't even know about an aberration calculation.
dude, you boys been cooking in the background. Um,
Yeah, we need
okay,
this for arguing with people online. It's very
for
handy.
for sure, for sure. Okay, so
Just today, we had a hypothetical where we reduced
Mhm.
75.75% of C. Would that change it? Sure would. Sure
Sure
would,
would,
bro.
sure would. And so when they move to the rest frame and moving frame of the sun, they end up accelerating the light. So they multiply C times N instead of C divided by N. Okay. And then when they do the transformation from there to back to Earth, they're like, oh, this creates no angle change. So they're like, oh, okay, that's how it works. Now, the issue with that is if you derive the speed of light using the geometric relationship on the sun requires superluminal velocities. And we've been pointing that out on Twitter. And one of the main primary lads that argues this was like, "Hey, I actually made a mistake at the end. Can you of my thing that I wrote where I was taunting you about this, and then you solved for it, and then made it obvious to everyone." So actually, I kind of get a little retraction in. The proper one would be just using v or yeah, the speed of light over n, which would give the normal lesser amount. But if they do that, then that predicts an angle change as shown by here, which is what the classic theory predicts, but that's not what's measured. So in order to, so they say, hey, you can't use any geometric relationships or consequences to derive superluminal velocities for our fictitious transformation to the sun to explain why there's no angle change as a function of a Lorentz transformation. But when you try and use the actual relationship, you can't do that. So it's this weird double standard thing. And then on the back end, they want to be like, okay, but also the speed of light in water, it's obviously slower. So just go ahead and hit the V over N there, my dude. but so which would in turn lead to an angle change. So you can't say that the geometric consequences in air is V over C aberration, therefore Earth in motion, and then say when we add water, there's no such thing as consequences for geometric consequences for relative motion and angles. It's like, oh, okay, dude. All right.
Yeah, what they said was nuh-uh, and you can't, and that's nuh-uh. Can't have that. That's just because globe. Dude, it's like one of the main. It's the only thing that they can point to since Mickelson Morley failed so spectacularly to be like, nah, we totally know Earth is moving. Look at this math I can do secondhand if I infer two other things. Like, well,
hilarious, dude.
I mean, you can do that. Like,
you can, but it won't help you. So it's like they're happy to use this as a placeholder for why there shouldn't be anything, but they accept none of the consequences or implications of what they just did to the speed of light in a rest frame. In a rest frame, it's accelerating through the light. I mean through the water. That doesn't make any sense.
wasn't there that excellent demonstration of the last who predicted there would be no change in water and then alarmingly saw like a very astounding and astute change when you put a laser thing and measured it with the laser rangefinder or something at the bottom of a water glass? He was like, oh, it dropped hugely.
Oh yeah, it was this through the looking glass.
I'm gonna find it right now.
Pull it up on the spot. Through the looking glass, double slit.
A really good demonstration of what we're talking about, and then it would be the exact effect they have to disqualify and be like, nah, that doesn't actually happen because watch my math. Ready? Boom, gone.
I timed light with my phone. And then she's like, I don't, and then she's like, I don't know why light slows down in water. And the reason she doesn't know why that's true is because what they to like forget about all this transformation, reference frame, sun accelerating, like that's going to lead that people are going to ask questions. Okay. What we can do instead is do relativistic velocity comp, and through the way that they interpret the speed of light being constant in all reference frames, they don't account for a refractive medium. So as you see in this equation here, there's no n. So they just have a cool 20 arc second there for as if there's nothing. So when they teach that to people as like physically meaningful, they're like, yeah, speed of light's constant and everything. It might, appear slow for fake, as like a not real thing or whatever. But then
it might sometimes appear not that way, but don't you worry.
Yeah, dude, look at her getting the ruler out. She's like, what? I just measured the speed of light and it's 3 inches off. Yeah, you can see the turmoil here.
It's 4 times
It's
either.
really
Even
long
though I
video.
have this very simple argument. Imagine we have about
4 times either.
even
Yeah, I used to have the exact
It does matter.
timestamp for it.
measured, but doesn't matter,
It does.
which is a bit that it takes.
Well, in any case, here's the Lincoln channel. So not gonna bother going through it all. But then she does a follow up here, and because there was some people in the comments were like, well, maybe the group velocity, wave velocity, phase velocity, blah blah blah
Well,
velocity.
maybe, yeah.
I was
Yeah,
convinced
yeah.
that
So your girl was like, actually, I had the one that you guys all said wouldn't do, wouldn't work or whatever. And then so like I had the correct one, in other words. And then she's like, 1 second here. And then she's like, uh, I'll redo it and buy the other one, and then they both give the same result. So one that reads off a group velocity, one that reads off a phase velocity, gives the same timing difference in water, leading to a different distance derived because of that timing difference. So she had to reconcile that this has no meaning at all, no explanatory power over anything, and so anyway, she went. You could see her go through that. It was really interesting.
You could see the struggle in the process.
All right. Well, we got a nice clean hour out of this one. So if there's no further questions, really, I think it'd be a good one to end on to keep it nice and tidy. We went over a lot. Quick recap here. All we ever had is observations from Earth, and using a ratio of pi and periodicity, physical parameters were established for orbits, and that line of thinking kept going and kept going, and new constants were introduced which allowed them to do new ratios, which allowed them to define other constants as a ratio of the other ratios, and it built not a system that's not only that appears to not be based on solely observation, but appears to be based on dynamic causes of an interplay of mass and gravitational relationships. But that doesn't appear to be the case, because as we just went through all of the backbone of all the complex math, none of it uses any dynamics. When dynamics are asserted, uh, another violation comes into play with the gravitational tensor stuff. So nothing actually satisfies any sort of dynamics in the sky. Everything works off of a ratio of periodicity and time, which allows them to solve for velocity, which is all anyone has ever had. No one has anything different. So yeah, hope you guys enjoyed. We'll be back on Friday for the Friday community Twitter space. Hopefully Twitter is a little more uh accepting of my internet browser or whatever issue is going on with it, but it doesn't seem to work on my phone or my browser. So in any case, we'll stop in and see what the lads are up to there on Twitter, and then we'll be back again on Sunday for Glowbusters with hopefully a surprise special guest presentation. So stay tuned for that.